the intro to this section on site assessment and planning. I showed this slide before, but it's pretty instructive in being able to talk about how these things look different, how they're structured different, and how all of the site planning strategies and the stormwater BMPs that work in tandem to provide the whole picture of low-impact development. The process is really talking about not saying, here's what we're going to do, but if you want to do a particular thing, showing why other things aren't feasible is going to be part of that process. So one of the ways to do that is to think about it as an overlay of all the existing information that you could possibly pull together. Obviously, there's certain things we look at before we start projects, like a survey, land use, zoning, utilities. Some of the things that sometimes get under-analyzed are things like existing vegetation and habitat, how the site will actually connect to larger ecosystems itself, looking at the idea of creating a site analysis that it happens informally or formally in a lot of projects, but really taking that layered approach of all the information that you can gather, pulling that all together, and then looking at areas where you have potential opportunities to focus on building. You have other areas for open space retention, and then areas where you could potentially site stormwater facilities, or thinking about them as distributed throughout. So this is a pretty traditional grid that you would see. If you go back to the previous slide where all that nice open space was on the west side, we just built all over all that and kept a few little remnant ecological patches. But one of the things that comes out of that is you get a pretty high level of impervious surface because there's a lot of roadways, there's a lot of access frontage. You're not really taking into account a lot of the site features. A lot of times this gets imposed on both existing vegetation, ecological systems, and topography. From a design and building standpoint, if you're trying to apply this to a site that has, say, a little bit of topography, you're talking about more grading to make the grades work, trying to figure out how to sort of level a site versus work with the existing topography. The good part about this is that from a planning standpoint, you have a lot of connectivity through the project itself. You have a lot of roadways and you have a lot of ways to get where you're going, but one of the things is you're balancing pros and cons of each development process when you do particular types of design. So another very common development type that we'll see is the cul-de-sac curvilinear development, but this would be another way of taking the site and looking at maximizing lot coverage. We have less roadways, so we have about 15 to 30% impervious area. We have, on all these scenarios, we have the same number of lots, so it's showing them relative to each other. It's maybe a little bit more adaptive to site features. You start bringing in curves and you start doing cul-de-sacs. You can work along contour lines and maybe develop sites that aren't as imposing on the topography. This, on the other hand, goes along the other spectrum of communities that are less connected. So this is part of the appeal for people in a residential standpoint is to have the cul-de-sac at the end of the street that can be the private space. But what happens often is it doesn't necessarily create this good space for social interaction, because a lot of times you'll have the big cul-de-sac, you'll have the houses in the front, and then everybody hanging out in their backyards in a residential model. The LID approach looks different. It's got a different feel to it. One of the things that you look at is reducing the overall amount of impervious surface. So in this case, the impervious coverage is similar, but you've reduced the roadway. You've reduced the amount of roadway throughout the project. You've made a lot more compact site development. You have the same number of lots. Typically what you do is you make smaller lots that each individual lot is smaller, balancing that out with the fact that you're protecting and providing an amenity of larger landscape vegetated space. The one thing that's the most important from an LID perspective is the fact that these project layouts can be very adapted to site conditions. So you can look at patches of vegetation and cluster development that fits within pockets. And there's some great examples of developments that are out there that have sort of still maintained the same number of saleable lots, but have also done it in a way that's a lot more sensitive to the land. These new development patterns is we have to provide all of that new landscaping. From a marketability standpoint, everything's going to be relatively young. It's not going to look very vegetated. You're also going to spend a lot of money buying landscaping to create an amenity on both of these. In this case, you're weaving it into the existing amenity that's already there, so it's a way to both leverage some of the natural condition and natural systems that are there, but also when you look at the smaller footprint, you're actually providing less developed landscape area, so it's both a more efficient way of doing it as well. When you start looking at cost benefit, that's a factor to consider. The idea of the traditional versus LID type development has some significant stormwater benefits as well. So you look at the concept of a conventional development, the idea of creating a regional detention facility that can accommodate the level of development that you're creating. You start looking at these giant facilities, which are both rarely, if ever, attractive or an amenity. They get the big pond with the fence around it. That's also displacing potential lots that you could be selling on a development. Reducing the actual development envelope itself, so reducing impervious area, using decentralized bioretention, minimizing excavation, making narrower roadways, and when possible, using permeable roadway surfaces results in a pretty dramatically different amount of stormwater management you would need for a typical project itself. Some of the typical layout strategies that we start looking at are being able to cluster development rather than just gridded streets and creating lots on both sides in development. And this is, obviously based towards more mid-density residential development, not high-density urban, but the idea is the same. Even on a high-density site, you can work with the site features to maximize some of the existing conditions and minimize some of the impacts. But clustering development actually, a lot of times it's done to protect trees. One of the things that's very interesting is to use it to focus development where you have soils that are maybe not good for infiltration or bioretention, and to leave your open space where you can actually effectively manage stormwater. So again, knowing the soils and the vegetation gives you an adequate picture of where to locate buildings itself. Grading to create smaller basins. By clustering development, you can create smaller footprints that can each be managed as sort of a smaller sub-basin or small watershed. When you have a smaller basin with less impervious surface, you have a lot of strategies that you can pull from the LID BMP toolkit. So you start looking at permeable paving and bioretention and flow-through planters and green roofs and all the things that, it gives you a lot of opportunity versus if you have a huge basin, then centralized facilities seem to make more sense in that way. Thinking about a similar sized project, you see the one on the left is looking at cul-de-sac development, a centralized facility where everything is flowing into one regional facility that's also, in this case, taking up lots that could be, sold as part of the development, versus on a similar sized project, breaking that into three sub-basins, weaving the bioretention and the stormwater management into amenity and natural areas that are existing on the site. So you've interwoven the landscaping, the amenity space, and the stormwater, and a lot of times can get better development and more lots out of it as well. How this looks in some particular types of development. The examples that we've talked about prior to this have been predominantly suburban, mid-low density development that looks similar to this. So one of the things that we talked about was roads, driveways, and parking. So strategies that could be used to reduce impervious area, cluster development, increase usable open space, and decrease site disturbance. What it also does is creates opportunities for community gardens, for connected parkways that kids aren't playing in the street, they're actually out, in open spaces, and from a marketing standpoint and being able to use this to entice potential buyers. It's a lot easier to sell something like this that has clustered development and open space versus something that has a really traditional suburban pattern. There's a lot of stuff that we look at before we start developing, but the process really is accruing and overlaying as much information as you possibly can. So it's not just the topo map and the program for how much we're going to develop and maybe a couple of geotechnical borings to tell us where we can do infiltration. In this case, knowledge is power. We have lots of opportunities the more information we gather to make a broad range of decisions. In this case, you look at geotech, wetlands. From a regulatory standpoint, these are the red flags that you want to be able to understand: unstable slopes, steep areas, wetlands that you might have to mitigate or work through buffering. The parts that we don't think about a lot of times are habitat corridors, large stands of existing vegetation or significant vegetation. And that's the part where looking at all of these things in concert really allows you to make those better decisions about what type of development you're going to create. Maybe the biggest stick in the state of ecology mandating some of this this information. I guess it's a stick that offers you a lot of carrots for how to get there. The idea of what you're required to do, and if we tell somebody to do a site analysis and we don't specify what that is, then you're going to get a very sort of varied and minimal sort of documentation of how people went through the process. In this case, the minimum requirements for small site is doing a survey, doing a contour map, topo, soils report, native soil and vegetation, and then a drainage report talks about the site plan. So that's for small scale projects. And then the difference between small site and large site, it's saying this is a bigger site, maybe the stakes are a little higher, but we're putting an additional burden on folks to do a higher level of assessment. So more in-depth geotechnical, this goes back to our question about soil variability, having all the information we need. What that does is gives us ammunition to avoid failures, but also gives us opportunities to identify potential areas.
What's shown there for the ideally in 2 phases, I think, is an important point, and one of the more key site assessment strategies in my mind is that, again, like septic systems, in my view, have typically done their soils assessment basically in 2 phases. Instead of just calling the geotechs up, they roll out there, they dig their test pits, and they write the report and they're done. This is really done best in 2 phases, where we do, just like septic, we go out and we do a reconnaissance level soils assessment with some hand augers. We poke a lot of little holes around, we review maps, we go out and confirm, we see what we're up against, and then we maybe do a conceptual site layout, and then we go back out and collect our design level information. And so really where there is a real reconnaissance phase and then more of a design phase. These infiltration reconnaissance can be done hand auger, or it can be done with quick vac holes. It's very common these days to go out and just get a vac truck and just vector boreholes to get a quick, rapid confirmation of maybe what the map soils are, and then do a conceptual layout, and then really to go back in on a second phase to collect your real design level information. And this is where we're going to be running pit tests and getting our design level information. So here's a summary of the kind of information that needs to be collected for the practices: bioretention, infiltration at the proper depth, also seasonal high groundwater. We have vertical separation requirements, so we need to record and understand the seasonal high groundwater, whether that's by soil modeling or through monitoring with a piezometer, what have you. And then permeable pavement comes along with a little more thinking because of the first bullet there, which is staging and access. So when we're doing our site assessment, it's very, very important for pervious pavement to understand those implications. Because pervious pavement often occupies a significant area, and it's often the area from which we want to stage materials and build the project from and access the site, it requires some thinking about how we're going to do that without fouling the subgrade. In my design work, that's probably the trickiest business. I think, a bioretention area, you can pretty well know where they are. It's a discrete area. You can fence it off and say, look, let's not even excavate that area until we're ready to build the facility. Let's do our early rough grading and just leave that area ungraded for now so we don't foul it up. But the pervious pavement can be tricky. And so thinking ahead about, well, let's, if we did a temporary construction access over here, we could do that. Or if we laid the site out a little bit differently where maybe some thing could get located that's temporary, and then similar infiltration at the proper depth, so understanding what our anticipated or top of subgrade, and then doing the infiltration test essentially at that horizon so that we're getting our infiltration rates in the right soil horizon, and then the pit test, depth to groundwater, and mounding. From a construction and development point of view, know that there's typically 2 rounds of testing that we want to do to be successful, and that we got to think particularly about access. Pit test, pilot scale infiltration test is really what's needed to get a design infiltration rate. It's not considered sufficient anymore to go with grain size analysis approach or even a double ring infiltrometer or some kind of a small scale. That I think the findings has been over many years that those are notoriously inaccurate, and that the only way to really get a true infiltration rate is to use the pit test method. And in the manual, there's a whole host of correction factors that are used to account for what type of test method and you're using and what size the tributary area is and so forth to correct these values to come up with what is thought of as the most accurate information. So there's some examples there to get a sense for how many of these tests are done. These typically are all day sort of tests requiring a water truck and a technician. You can see there for a larger site, we're talking about one every 5,000 square feet or so. And then for building facilities along a roadside, one every 200 feet. These are just guidelines to give you a sense of how many of these tests are necessary to complete design.
You're doing a pit test every bioretention in your site. You're doing one every 5,000 square feet. You're getting really finer grain information than if you did a couple distributed around a large site. And then for linear sites, the idea of doing it every increment to get that site scale data, because you might get that regional variation that could contribute to one facility doing great and one a block away doing terrible. Giving you an idea, in this case, the diagram you see, maybe if you are looking at siting and doing a site plan and you want to maximize infiltration in a certain area, the dark blue area is the highest infiltration rates that a particular site would have.
Where bioretention is not required. It's not a determination to say you cannot build bioretention in soils that infiltrate less than 0.3, because technically you can. And I have worked with geotechs very comfortably down in the very small numbers, and you can design accordingly. That's the threshold from a policy point of view that has been established, where if your initial infiltration rate is 0.3 measured by your geotechnical engineer, ecology says you don't have to do bioretention. Above 0.3, you have to do. You must show when we go through the list 1 and list 2 process. And permit feasibility versus, it's not a technical feasibility limit. Because if you're willing to put a little extra storage under your pervious pavement, you can work with infiltration rates less than that. That's fine. That is before the correction factors get applied. So the way this works is that you get your short-term infiltration rate, which is what they measure in the field, and then you go back and you apply correction factors to it depending on the size of your contributing area and some other factors to get down to what is considered a long-term infiltration rate, because they assume a degradation of the infiltration rate over time. So the correction factors used to be basically, depending on the size test, if you did like a relatively small scale test, it was a safety factor of 4 and 2, and now there's a little more of a nuanced set of correction factors. But suffice it to say, that's the infiltration rate that they measure with the pit test in the field. And then you go back and you say, well, if I've got a relatively small amount of contributing area, I apply these certain factors, which give you the long-term rate. And the long-term rate's the design rate. And that's the rate that's expected to be at the end of the life of the facility after it has a certain amount of expected clogging.
This is a Broadview neighborhood in North Seattle. The Green Grid project that was implemented a few years ago. This is an example. I don't know if you can see it. There's 3 sites that are within about 3 blocks of each other. And you look at the variation that exists within a very small area. Site number 1, and this is a project that was implementing street bioretention facilities. The first site had loam, the second site had sand, and the third site had glacial till that was highly compacted. This is all within maybe 1,000 feet of each other. So that sort of internal variation. So that goes back to the fine grain and how much infiltration testing you need to do to make sure if you are siting bioretention facilities, once you've gone through that initial design process and you know where a facility is going to be, making sure you're definitely at least testing there so you know that the performance that you're estimating is going to align with that.